For page 3, you'll title it Parent Functions. You've already created your 2 books by cutting and folding the 2 sheets that I gave you with your parent functions on them. So for the first book, I want the one that has the linear and absolute value as your first 2. And so these are 2 of your parent functions. The linear function is f of x equals x. These are some values that I plugged in to this to get out the output. So this will be the input or the domain, and then these would be the range. So if you plug in -2 into the linear function, you get back out the exact same thing, and then so forth. This is also called your identity function because you get out the exact same output for your input that you put in. When I graph these, this creates a straight line with a slope of 1 that passes through the origin. The domain is all real numbers, and so is the range. For the absolute value function, this is going to take all of your values and make them positive, whether they're positive or negative. So when I plug in -2, it'll come out +2. When I plug in -1, it'll come out +1. And then these values will remain as is. And so when you graph this one, you're going to get a V-type shape. The domain is all real numbers, and the range is y is greater than or equal to 0. For your quadratic function, you'll plug in these values and you'll square them to get out these values. The domain and range is the same as that of an absolute value function. For your cubic function, you'll take the x values and you'll cube each of them to get out these outputs. When I graph them, I'm only able to graph 3 of them. And this is the shape that you get. The domain and range are both all real numbers. For your square root function, this time there are no input values. You're going to want to make sure to include only positive values and 0. And plug in ones that are nice. You could definitely do the square root of 2. It's 1.414. And then continuing. You could plug in 3, you could plug in 5, but I went ahead and chose nice perfect squares so that my output will be nice whole numbers. I'm also able to plot only 3 of these, and when I connect those dots, it looks like a shape like this. The domain and the range are both all real numbers. I'm sorry, the domain and range are both greater than or equal to 0. For your cube root function, you want a value for y such that when you multiply it 3 times, no, I said that wrong. You want a value for x such that when you multiply it 3 times, it gives out the value that is your x. I definitely said that wrong again. I was so sorry. You want a value of y that when you multiply it 3 times, it gives you the cube root of x. So for example, -8. When you multiply -2 3 times, you will get out -8. Now you could do the cube root of 5, you could do the cube root of 7, but again, I chose very nice numbers. You'll notice this time you are allowed to plug in negative values for x, unlike the square root function where you are not able to do that. So I did choose negative values as well, and this is the graph that you get, whose domain and range are both going to be all real numbers. That book is now done, and then we'll move on to the next book. Now these are a little bit more difficult. Your first one we have is the rational function. It's just 1 over x. This is also called the reciprocal function. I can plug in any values that I want with exception of 0. 0 is going to be an undefined value. I wrote that as UND. And this is going to create a vertical asymptote. We talked about that last week. When the bottom becomes 0, you can either create a vertical asymptote or a hole. And in this case, we've created a vertical asymptote. Once I plot these values, that vertical asymptote that I had at x equals 0, I've dashed that in. We'll talk about horizontal asymptotes at another time, but this is going to have a horizontal asymptote at y equals 0, so I dashed that in. I have 4 dots that I can plot, and then I'm going to connect them, and this is what the graph's going to look like. The domain and range are both x is not equal to 0 and y is not equal to 0. The greatest integer function, what happens with this one, it's going to take the value, so in this case -2.2 or -2.1 or -2.9. It's going to take the value, it's going to round this, in this case, down. So it's going to go from -2.2 and it's going to go to -3. In this case, it's going to be negative 1.9 or negative 1.8, negative 1.2. It's going to round down and go to negative 2. Negative 0.5 is also going to round down to negative 1. Regardless of what the decimal is, it's going to round down to the next integer that it's smaller than that. And it's got to be with no decimals on it. 0.2 will round down to become 0, and then 1.3 will round down to become 1. So this is your greatest integer function. It's also called a step function. So when I go to graph, for example, negative 2.2, negative 1, negative 2, and then negative 2.2 would be right about here. And then it's going to go down to negative 3. 1, 2, 3. So I would graph negative 2.2, comma negative 3. Every value between negative 2 and negative 3 is going to become negative 3. So whether I have negative 2.1, negative 2.9, negative 2.5, all of them will round down to become negative 3. And so I'm going to graph this as a horizontal line for those decimals. And then at negative 3, it becomes exactly negative 3. But at negative 2, it is an open circle. There's not going to be a value there. And that would be true for the positive values as well. So if this is the origin here, let's say I did the 0.2 one here. So here's the origin, 0.2 is here. And you'll notice that it rounded down to 0, so therefore I'm going to plot 0.2, comma 0. That's going to be true for 0.9, 0. 0.1, 0. So there will be a horizontal line at y equals 0 for all the values of x between 0 and 1. Where you're not going to include 1, it's going to be an open circle, and it's going to be a closed circle for the value of 0 itself. So for example, if I had 1, 1 would remain itself 1. And so there's going to be a dot at closed at 1, 1, but open at 1, comma 0. The domain is going to be all real numbers. Even though you have infinitely many holes, there are values that are going to be closing it in eventually, which are these guys right here. So the domain is all real numbers. And then you'll notice that I don't use all of the y values. I only use the ones that are the integers. I don't use any decimals at all. So this is the symbol that you have for integers. So this is saying y is an element of the integers. We'll get to exponential growth and exponential decay eventually. So for this one, I am graphing 2 to the x. This could be 5 to the x, 9 to the x. It can't be negative, it can't be 1, and it can't be 0. But any other value can be here, and I chose 2 to the x in this case. So these are the values that you would get out for that one, and I've now graphed them. There's your domain, and there's your range. For the exponential decay, I'm choosing a value between 0 and 1 this time, not the value of 1 or 0, and not a negative number. So this time I did 1/2 to the x. I did the exact same thing. I plugged in the values for x, and then these are the y values that you'll get out. If you don't understand how to get these values for now, it's quite okay. We'll talk about them in class when we start transforming these graphs. And so this is going to be your exponential decay function. For these values, again, don't worry about how these values are coming about. Just plot them for now. Do the ones I have in my book, and then plot them, and these are your domain, and these are your range. Don't worry about how to come up with these actual values for now. Okay, and that is it for this page.